start. Today's topic is neural networks, and I would be diving deep into it, like what are neural networks, the history of neural networks, what is the present day scenario, and what are the future prospects of it. So, first, let's talk about the history of neural networks. So, as the name suggests, neural networks. The word neural has come from neurons, which are the basic units of the human brain. So, what can you first imagine when you heard the term neuron? You think that a neuron is some unit which transfers message from one point to the another, right? So that's what human brain does, transfers messages from the neuron does that, transferring messages from one part to the another part of the brain. Why does it do that? It does so that it can make decisions based on that transfer of messages. Like if I'm taking a decision, then I have to think about various prospects of the decision, that what can possibly go wrong, what are the possible options for me, and then I can take the decision accordingly. So the scientists during the 20th century, what the scientists were trying to do is that they were trying to replicate the human brain. They were like trying to find new research, like new. They were trying to find new path through which they can crack the human brain. So during that time, a few bunch of scientists, what they were trying to do is they tried to make a artificial kind of model. The artificial model, they named it a neural network. It was the idea has been drawn from the word neuron, so they have named it neural network. And what this artificial neural network does is it tries to replicate the human brain. I won't say it's completely the human brain, because it's not possible to completely replicate the human brain. Even now, it's totally difficult to completely replicate the human brain. So it tries to make a rough estimation of what the human brain does. So from that, we have come to the term neural nets or neural networks. So, as I was mentioning, the various applications of neural networks, like big companies like DeepMind, Baidu, and likewise, companies are working on deep neural nets. And to know more about what is deep learning, what is how it's different from the machine learning, we have to dive into the key building block of the deep learning module, that is neural nets. We have to first know what are neural nets. So we will walk in a sequence where we will first see perceptron. So first, when the scientists were trying to replicate the human brain, first they came across perceptron. So what are perceptrons and what they do? So perceptron, as you can see from the diagram, is like a node which has a few inputs to it, and based on that few inputs, it's giving an output. Now, from based on this slide, you will be totally blank. Like, what is this x1, x2 coming in and output going out, and this threshold? What are these terms? So you need not worry. Let me give you an example to make it clear to you. Like let's suppose today I have to make a decision. Today morning I woke up and I have to take a decision that whether I would go to attend the class. So that's a decision I have to take. There can be two possible outcomes. I can either go to the class, or I may restrain from going to the class. I can just sit back and see, like I may or may not go to the class to attend the lecture. So how can I make the possible decision that whether should I go to the class or I shouldn't go to the class? So my decision would be based on a few factors, like what class is it? Like, is the class interests me? Like the topic being taught, does it interest me? And there can be queries like does the assignment given in the class completed by me? Like, if I haven't completed the assignments already provided to me, then it's no point going to today's class, because I won't be understanding what the professor is teaching in today's class. That can be a possible thing to ponder about before taking a decision. So what I'm trying to say is, like, whenever you take a decision, you have to think about few criterions based on which you take the decision. So a perceptron, you can imagine something like that. This output can be the decision you are making, and this x1, x2, x3 are parameters, like based on which you can decide whether you will take this particular decision or not. So as I was mentioning, there can be a criteria like whether I should go to the class is based on the factor that do I find the class interesting or not. So let's suppose this x1 in the figure, this x1 is the criteria that do I find the class interesting or not. Now I have to give weightage to this. Like I have three factors, x1, x2, x3. Now I have to give weightage to each of my decision. Like, is the subject interesting to me? Have I completed the previous assignment? And third is like, does professor take attendance or not? Like, is the attending the class very crucial for me or not? So there can be three decisions. Now waking up one morning, if I think that the class is not that interesting, okay, so first criteria on which I am taking a decision is, say, suppose it's zero. Now the second criteria upon which I'm taking decision that whether I've completed the previous assignments or not. That too is no. I haven't done anything. So my two inputs are null. So basically my output is supposed to be zero. That there is no, I have no interest of joining the class and I haven't done the previous assignments. So at present I would refrain from going to the class. I would stay back. So that can be a possible scenario. Another scenario can be that I have done the assignments and I find the class very interesting. So I would like to go to the class. So the inputs are yes, yes, positive inputs. So I'm getting a positive output. That's what the perceptron is trying to replicate. That I am making a decision, and that decision is containing a weightage, like how much important that criteria is to me. Like there are two criteria, that have I completed the assignment and have do I find the class interesting. There can be a third scenario, like I find the class very boring and I have done the assignments. Then in that scenario it's really tough for me to make the decision, because I haven't completed I have completed the assignments, but I am finding the class very boring. So it might be that I might go to the class or I may not. So the decision is little bit complex to me. So as you can see, this term on the right part of the slide, WX. So what is this WX? Actually, this X denotes the criteria upon which I have to, based on which I am making the decision, and weight WJ, it is the it is the uh, how to say, like it's the weightage I am giving to that criteria. Like, am I considering the class interesting? That question, that do I find the class interesting? How much important that criteria is me while taking the decision? So I'm giving a weightage to that decision. So based on this, like if I consider these two inputs, and based on this, if I ask myself that should I attend the class or not, then I would get a response, a positive response or a negative response, which is actually zero. So that is what a perceptron does. Like it takes few inputs and gives an output, which can be zero or one, right? So yeah, before moving to the next part, I would like to hear from your end, like how much have you got? Like, what's your take on this? Like, is it clear to you or not? So I'm getting a clear response. So should I continue? Okay, so when it is asking, is this give output only 0 or 1 or yes or no time? Actually, it can be 0 or 1, or it can be yes or no. But it actually giving binary output. It can either give 0 or 1 or yes or no. So when I'm making a decision, it will be an yes or no. Or you can represent it in the form of 0 or 1. It can give this kind of outputs only, 0 or 1 or yes or no, binary output, nothing else. If you're clear with it, then can I move on to the next part? Okay. Fine. So next, move on to the next part. So next part is you can see, like from the previous one, it was just a single circle which was taking inputs x1, x2, and x3 and producing an output. but in this one you can see three circles in the initial part, then four circles followed by another circle. So what is this like? How it is different from the previous one? It's different in this way that here you are giving few inputs to this. Let's call the three circle part the first layer and the four circle part the second layer. So you are giving inputs to the first layer and you're getting some output in the second layer. So what does this signify? It signifies that say suppose you are making a decision. Like I gave the example of attending a class. So attending a class is a very simple scenario where you have a few criteria, and based on that criteria you make a decision that whether you should attend the class or not. But in complex scenarios where the decision can be based on a lot of factors, say suppose like in this one there are three circles in the first diagram, and in each of the circles you can see a lot of arrows going in. So each circle denotes a particular decision. Like it's an hierarchy of decision. Like you can't take a single decision based on a single output layer. You have to take the decision based on the outputs of various layers. Say suppose the first circle gives some, like you give few particular inputs to the first circle, it produces some output. Likewise, the first layer produces few output and it passes on to the second layer, and the second layer then uh, takes this output, like the output of the first layer, the decision taken by the first layer, and further makes decision. It's like let me give you an example. Say suppose in your life a complex decision has come in front of you and you are hesitating to make the decision on your own. So what you do, you ask your parents to help you out. So the first layer is actually like the parent. The parent, they are experienced, they are more experienced than you. So what they can do is they can provide you more insight, and based on that insights you can make a final decision. So here also what it does is, when the situation is really complex, a single neuron, these circles are called neurons, so a single neuron can't take the decision. So what it does is it takes the input, the parameters, and it takes a decision which is not the final decision. It takes a decision and it passes the decision to the next layers. Later on, you will see that these decisions are actually called activation, where the layer passes this decision to the first from the first layer to the second layer, which is also called the hidden layer, and from the hidden layer it passes the decision to the final layer, and the final layer is actually then taking the decision, the final output. So it is like that. So the importance of the second layer is that it adds more features to your decision making. Like when you are taking a complex decision, it can't be based on a few factors. It has to pass through a lot of layers before, after which you can actually take the decision. So that is the importance of the second layer. When you will dive into deep learning, or you will be seeing code and neural network architecture, you will be seeing layers after layers of nodes, and a lot of inputs are being given to that nodes, and finally an output is produced. So the more complex the neural network, or this network, the more complex this architecture is, the more complicated decisions it can make. So that's what's the importance of the second layer. Now moving on to the next layer. Now let's do a fun thing. I would be sharing this link, okay, with you. You just open the link and just play with this. This is a cool site where you can just. I would be showing you, and I would also be sharing the link. Mm, okay. Wait a second. Share the link first. Can you see the link? Uh, I would like you to just go to that link and play alongside. Then it would be a fun thing to do. Like I was mentioning that there can be few neurons, and based on that neurons there can be an output. So as you can see in this layout, there are few features. You don't have to understand what features are. Let's just dive and let's just concentrate on this part. See, I have included four neurons here. There are two hidden layers. In the first layer there are four neurons, and in the second layer there are two neurons, following which there is an output. Let's see what happens when when we are using this architecture to predict something. You can see certain blue dots are there, and certain yellowish dots are there. So, and there is a white line which is partitioning them. Right side is blue and the left side is orange. So you can see that a model can actually make a clear-cut differentiation between this is blue and this is orange. So when I considered four neurons, this is the output I am getting. Now let's try, say, suppose, let me try and reduce the neurons. Let's say I have got one neuron in the first layer and the second neuron in the second layer. And let's do it again. Let's run it again and let's see what's the difference. See, if you have noticed, the white line has decreased a bit down. Let me take another example. Okay, let me take this example, then it might be clear, more clear. See, as you can see that mm, the model is getting trained and it's taking a lot of time, because see, the pattern of data is really complicated. So the model is taking a quite a few time to actually partition the blue dots and the orange dots, and it's not actually quite good partition as well. Like in the middle layer it has given a blue line, and on top of it there is an orange part, and below it there is an orange part. It is considering only one neuron. Now let's see, if I increase the neurons, does it produce something better or not? Let's try again. Alongside, you can also try an experiment on your part as well. It's quite a interesting thing to do. Now see, as you can see, I hope you are able to understand that inside there the blue dots are being partitioned, and then you can see that orange dots are also being labeled as orange, and following which there is a blue line, blue part. So partition is very clear in this one. In the initial one, the partition was not that good. So, as I was mentioning, when the features are complex, like these features are really complex, the dots, the way the dots are arranged is really complicated. So, in that case, in that scenario, if you use just a single neuron in the hidden layers, then the partition would not be that great. But when I was using this one, yeah, when I was using this one, then you can see there is no such clear difference. When I am using five neurons in the inner layer and five plus four neurons in the hidden layer, then the output line which was being produced, and when I was using one neuron in the hidden layer, the output that was given to me, that was not very different from one another. Why is that? Because it was a simple decision to make. And when the decision is simple, the neural network need not be that complicated. But when the decision itself is complicated, like in this one, the decision is itself really complicated. So in that scenario, if you use just a single neuron in the inner layer, that won't produce good outputs. So I have to increase the output, the hidden layer neurons from 1 to 5. So in that scenario, I am getting a good result. So okay. Now I would like to know from your side that how was the how was the simulation? Like, did you understood the difference between a simple scenario and a complex one? Audience is silent now. Okay, when it is saying not very clear. So should I repeat this part, the simulation? What's your call? Like, should I repeat again to make it more clear? Okay. Agusip is asking, does total number of neutrons only matter, or their distribution is important as well? Actually, their distribution is also important. Like in this scenario, like in this one where I was using just 5 plus 4. Let me go back to this. Yeah. So in this one, when I was using this 5 neurons plus 4 neurons, in that scenario, the output was something which you saw few minutes back. But when I'm using something like this, say suppose I make this 4 and I make this 5, then the output produced can be different from the initial one. there are two hidden layers, and if the if I first use 4 neurons and then 5, then the output produced might be different from the one where I am using 5 neurons followed by 4 neurons. So that's a architecture specific thing. You need not go into that detail. But let me explain this part once again. You watched carefully. Like, what's the difference? See, now I'm using, okay, let me make it more simple. I'm just using one layer, one hidden layer, right? I'm just using, this is the input. You don't have to understand what is this features. Let's say that this is the input I was giving, I was explaining in the previous slide. This is the input, okay, and this is the neuron, this one. It is quite similar to this architecture that we are giving three inputs. There is a node and it is producing an output. So it's quite similar. We are giving four input. In this scenario, we are giving four inputs. We have got one neuron and we are producing an output. In this scenario, the output is we have to make a decision that in this one decision is that we have to partition these blue dots and the orange dots. That's the decision we have to make in this scenario. So let's run for this one neuron and see how's the partition. So you can see the partition was made very clearly. The blue dots and the orange dots are clearly partitioned in this one. Okay, so we can use this architecture to partition these dots, right? Now let's try something different. Now let's say we are using two neurons. Let's make the architecture a little bit complex. Earlier I was using one neurons. Now I am taking two neurons and now I run the machine. Now you can see that the output produces again the similar kind of output. Like, the partition is still good. Maybe the white line got shifted a little bit, but still the partition is quite good and it's similar to the previous one. So in this scenario, it's quite difficult for the human eyes to say that whether a difference was made or not. But yeah, so in that scenario, like in simple decisions like this, where you have to partition dots like this, where blue dots and orange dots are very clearly partitioned, in that kind of scenarios, a single layer, a single neuron can produce output which is quite similar to two neurons. So it's a simple decision. So in case of simple decisions, you can use an architecture like this. So this is the architecture you can use in case of simple neurons. But when you have to take a complicated decision, then you have to use architectures like this, like really complicated, which would go above your head, architectures like that. So decisions like this, like if you can notice, taking a decision in this scenario is quite difficult because blue dots are followed by orange, then it's a spiral thing. So a clear cut partition cannot be made. Like, if you are thinking that you will make a straight line partition or a curl or something like that, it's a really tough decision to make. So in that scenario, if I use a very simple architecture like a just a one neuron, like in the slide you have noticed, like a one neuron thing, if I train this and try to get an output, you can see you have to wait for a few minutes because you have to make a complicated decision and just a single decision taking neuron is present. So we have to wait. But as we are waiting, we can see that the partition is not that great because the orange, there you can see there is an orange tinge at the top part of the screen which is covering the blue dots as well. So this is not a good partition we are making. Like, this kind of partition can't totally partition the yellow dots and the blue dots. So a simple, you can clearly see that a simple single neuron can't take a decision for you to partition the dots. So what you have to do is I have to increase the number of neurons. Say suppose I have made 4 neurons. Now let's see what difference is being produced. Now you can see that a blue tinge is being produced. Near the blue dots, a blue tinge is produced, and around the orange dots, there is an orangish part. See, likewise in the below part of the diagram, you can see that it's being covered, completely being painted blue. So this is clear, this is a quite good partitioning. The blue dots are being marked blue and the orange dots are being marked orange. So this is a really good partitioning. But in the previous one, we just saw that just a yellow tinge was there on top, at the top of the figure. So that's the difference between a simple architecture and a complicated architecture. When you have to make a really complicated decision, then you have to use architecture which is quite complex. Like in this scenario, there are 4 neurons, which is quite complex in comparison to the one we were using in the previous one. That is this one. Here we were using just a single neuron for making simple decisions. But in this one, We are taking a collection of nodes to make a complicated decision for us. So in that scenario, we have to make an architecture like that so that we can clearly partition the dots. Okay. What's the difference if inner layer is lesser or greater than outer? Actually, that's an architecture specific question. Like if I use four layers, as I was mentioning, that if I use four layers in the initial part and five layers in the second layer, or vice versa, then there will be differences which you have to try out. That's why I've shared the link with you. You can try this. You can go there and play with it. You can clearly understand that changing the architecture changes a lot of parameters. Like a decision in the initial one will be totally different from the decision in the next one. So I guess your doubt is clear now. I'm talking with Shayok. Next one is here what represents x1 or x2 on that one. Okay, so there x1 or x2 actually, like if you have noticed in this one, if you have noticed, uh, here I mentioned x1, x2, x3, and in this one, as I mentioned, don't look at this features part. Let's imagine this is x1, x2, x3. So this is actually acting as x1, x2, x3. When we will dive more into this in future sessions, might maybe, then we might see that what is this x1 square, x2 square, and what they are doing actually. But for today, just for the introductory session, it's not that important. So let's just take that it's x1, it's x2, and x3. I hope your doubt is clear. Okay. So I would like to know from the audience that if you're clear with this part, then we can move forward. Like if you understood the basic part. Okay. Okay. So moving on to the next part. Okay. Cool. So next part is So the next part is sigmoid neurons. As you have noticed in the first part, we called this perceptron, this circular things as perceptron, this node as perceptron nodes. Now, what is a sigmoid neuron? A sigmoid neuron is a similar kind of thing, like you have noticed in the initial parts. A similar kind of thing is sigmoid neurons. And what is the difference of a sigmoid neuron from the perceptron is that it's it's using a function, sigmoid function, to make the output better. Like let's move on to this one. See, like I mentioned in the activation, I have used sigmoid. Okay, like here you can mention activation functions and uh, use it to experiment with it, sigmoid or ReLU or something like that. But in this one, like as I was mentioning, this is the sigmoid function. So let's try to understand what's the difference between a sigmoid neuron and a perceptron. So in real world, while you are taking a complex like a decision, like you have made a decision, and based on that decision, like in this one, like you are passing some inputs to the first layer. Based on that, an output is produced by the second layer, and finally an output is produced. In this scenario, if you imagine that some node is actually behaving in a strange way, say suppose the second layer some nodes are behaving in a strange way, then it might be possible that the output can change by a great factor. Like I change the output, like I have made a decision in the first layer, I pass the decision to the next layer, and in that layer the machine is making a really complicated decision, and I have made the decision making really tough. Like if the decision should have been, say suppose 0, in the second layer the machine behaves in a strange way and it produces an output, say suppose 1. So that was a problem with perceptron. Perceptron behave in a very rash way, like a single change, like if from the first layer, if a single slight change comes to the second layer, a great margin of error can be incorporated in the final decision making. So what scientists decided that let's not use the simple perceptron, we will use Sigmoid neutrons. So what Sigmoid neutrons does is it's similar, like it's really simple. Let's just walk along. See, like in the previous one, what we were doing was, like if you have noticed in the previous slides, I mentioned something called WX. So what was this WX? This X1 was an input to this model, and W was a weight associated with this path. So as I was mentioning, while you take a decision, your decision is depending on a factor, and you give weightage to that factor. Then how important is that factor to you? So that was WX in that scenario, and that was producing a certain output. And in this one, what we do is we do a similar kind of thing. We are taking the WX and we are passing it to a function called Sigmoid function. So let's not dive deep into what this does, but actually what it is doing is, in a simple terms, what it do is it simplifies the graph. Like in initial scenario, if wx was producing very scarce results, like for a simple change in the wx value, a great change in the output was being produced. So what we have done here is we have normalized the output. Like this curve, if you can see, a sigmoid curve looks like this. So let's take an example. Let's say on the x-axis we take value close enough to 0, something below 0, and we take another value which is more than 0, but it is also close to 0. So in both the scenarios, if you can notice, the y value of the curve is nearly close to the value, to the previous value, like something for some value of x below 0 and for some value of x greater than 0, the value being produced on the y axis is very near. So that is normalization. What is normalization? Like for small changes in output, for small changes in the input, the output does not vary that much. So if we imagine that we are giving an input to the neural network, say suppose minus zero point 0.1, and say suppose we are giving an input to the neural layer of plus 1. So for both of them, the output will be close enough to zero point 0.5. So that property of sigmoid we are using here. Let's not dive deep into the mathematical part of it, but for the timing, let's understand that it is adding a normalization to the curve. Like similar kind of thing. What we were doing here, we were giving an input and producing some output. A sigma neutron is similar to this, just a small difference that it normalizes the input. Like when I am taking a decision, it normalizes my decision. Like it might be that my decision is very biased decision. So what it can do is it takes the decision and uses a function to normalize my decision, so that the output produces not very rapidly changing. Like if I change a small parameter, the output might not change by a huge factor. Like as I was mentioning, the going to the class example, like a simple decision, like whether I have done the assignment or not. In perceptron model, if I notice that I haven't done the assignment, then it might be possible that the perceptron output might be that I won't go to the class. But when we apply sigmoid, then we weigh in a lot of factors. We try to notice that, is the class really important? Like not doing the assignment, is it really that much important to me? Like should I not go to the class? Just because I haven't done the assignment does not mean that I won't attend the class. So sigmoid is like that, that it tries to normalize the decision and does not take decision in a rash way. It just weighs in all the possible parameters and takes a final decision. Again, I would like to know from your side, like, was it clear or not, or completely went above your head? Like if you have any doubt, you can write in the chat. We will be looking into this in a lot more detail. Like today, I have intentionally not mentioned the mathematical part of it, because in the initial lecture only, if I include a lot of math, it would be really complicated for you to understand. But in the later sessions, we will be covering the mathematical aspects as well, so that it's little bit more clear. But for today, let's just understand that it's a normalizing kind of thing. It normalizes the decision making. Moving on to the next part for today, which is the gradient descent. So, what gradient descent does is, let's suppose you are taking a decision, right? You are making a decision that you will go to the class or not. Maybe that might be a correct decision or a wrong decision, but you have to predict, like a model predicts, no, like any model, like a neural network model, it has some predictions. In the equation below you can see that yx and a I have mentioned. So what is this yx is actually the output the model should have produced. Like I have given some input and the output should be yx, but actually what happens is, like, some due to some biasness, due to some problems in the training, the model produces output, say suppose a, the output produces a. So clearly there is an error. You can notice there is an error value. Like if the output should have been 1 but the output is 0, then there is an error of 1. Likewise, if we are training on a few examples, like there are 10 decisions I have to make on a given training input. On the 10 data, say suppose the first one there is an error of 1. Similarly, in the second one there is an error of 1, but in the third one there is no error. Likewise, we calculate a cost function. What is this cost function? This cost function tells us that how much distant is the output produced from the output it should have produced. Like yx should be the output produced by the model, but it is actually producing a. So there is a clear cut difference between the output that should have been produced and the output that is being produced. So by squaring that and summing it over, we are finding out the cost function. Let's not to get into detail that why we are summing and doing a square, but just understand the basic intuition that if there is an output being produced and there is an output that should have been produced, so there is a clear cut difference between the desired value and the arrived value. So taking a different difference of these two values, we can get a cost. This cost is actually the error value of the machine. We can say that this machine is producing this much cost or this much error. This model is producing this much error value. So squaring it over, we have derived a function which tells us that this is the cost function of the model. Now, as a scientist, what you would try to do is you would try to reduce the cost function or the error in the model. You would try that the a value is as much closer to the yx value. So what I can do is I can try and make the model better. So as a human, you can try to make amends to the model and make it better. But how will a model understand that it is making error? So what it does is it takes this cost function and it tries to minimize this error. And yeah, to minimize this error, let's suppose this is a function, right? This is a function. So the function can be plotted on a graph. Say suppose the function is plotted like this, the one are being able to I hope you are being able to see the one in the figure. This purple figure, this is actually the curve. So let's suppose the curve for this cost function is this purple thing. Now we have to minimize this. In earlier classes, you have learned that to minimize a function, you find the derivative of that function. So what basically gradient descent does is it actually finds the derivative of the function and tries to minimize the cost function, but in a way that all the parameters are being included. Let's imagine, like, if we don't think about the mathematical part and just take the intuition, like if this is a cost function and we are trying to minimize it, then we can imagine that initially the cost function is really high, so value is somewhere near this 2 value or more than that. So we can imagine this as a hill, like we are standing on top of hill and we are trying to go down the hill to the valley. So the valley signifies that there is no error and top of the hill signifies that there is a huge margin of error. So how can we reduce this error? What we can do is, if we can imagine that we are rolling a ball from the top of the hill and try and push it down the hill to the valley. Like in this figure, if you can notice, it is the 2D view of the same thing. Like if I have a ball which is on the top of the hill and I roll the ball down the hill and try to bring it to the valley. Like in this graph, you can notice that there is a point marked as M6, FM. if we try to bring the ball to that point, what we will do is that we will roll the ball down this function, and I would like to bring the ball close to the point which is marked as M6. But as you have noticed in real life, when you roll a ball in a curve like this, a curved surface like this, the ball first rolls down and then starts up, getting up the other way. Like it will go down one way and it will again go up the other way. Like this, it will keep oscillating near the point M6, FM till it finally reaches to a stop at the point M6. So we can imagine a gradient descent in a way like that. That it's a ball rolling down the hill and it tries to reach the valley. So what is gradient descent? Gradient descent is trying to reduce the cost, and by reducing, what I mean is that it's trying to go down the hill, down the hill, and tries to get to a point which is marked as M6, FM. Okay. So as you can see, I have mentioned guess next step. So what it signifies is that while standing at a particular point, I would try to see that in which direction I have to go. Like I have to make a guess. I am making a guess that I have to go down the hill. So the ball makes a decision and it goes down the hill. Similarly, the model makes a decision that the error value should be reduced. So the ball goes down the hill. Likewise, it goes down, 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 and finally, when it's around the point M6, when it can see that the error value has reduced a lot, then it can finally say that the cost function is reduced to a value which is optimal for our use case. In that scenario, I would say that the model is optimized or the model's output is suitable for my use case. So that's what a gradient descent is. It tries to reduce the error in the function, this cost function. It tries to reduce the error in this cost function, and the cost function is actually the difference between the desired output and the output that we are getting. So I hope this part is clear, like error. And I would like to know from your end, is it clear or not? Venus is saying in linear regression. I'm not sure what you mean. What are you trying to say, like in linear regression, which part? Right. So this is pretty much the thing I wanted to share with you today. So if you have any doubts, you can write in the chat. We can go back and discuss few things if you are not clear with it. Yeah, there are detailed material, like you can follow course on of Andrew Ng on Coursera, learn machine learning. I would be sharing this on the in the group, various groups. It's already available. GDSC team would be sharing that too again. You will get access to it and you can learn from there as well. Okay, you need not understand what's B and NA here. It's just a mathematical representation of the cost function. Actually, if you want to know like WB, like this B is called the bias, W is called the weight, and this N is actually the number of training examples. Like when you train a model, you are training on a few sets. So N denotes the number of examples, and this B is the bias. The bias is associated with the model. The weights, like the W is the weight, as I was mentioning WX, and this bias is the biasness produced in that calculation. So that is B, and yeah, you need not go into that much depth. I was just giving the basic intuition, like what is the gradient descent and how we can reduce it. Okay, so you can share your doubts now. I would be taking your doubts. If you have any further doubts, or we can end the session for today.